Hello, dear students. So I welcome you all to the next session and the last session of Electrostats chapter. So, dear students, what we have done until now is that we have learned the theory of this chapter, and today we are going to practice some fabulous questions from the theory that we have learned. All right. So, without wasting any time, let's get started, everyone. And just in case if you have not subscribed the channel, please do it right now. And if in case if you do like the session, then hit the like button, okay, and share with other students as well. All right, people, so we'll start. Okay, so I'm going to give you first question now. Okay, so in the previous class we learned about the concept of electric potential, and we learned that this concept helps us to write the potential energy. Now, what is the use of writing the potential energy? So we want to use work energy theorem, and to do that we need to be able to write the potential energy. So let me show you what kind of questions can be there, and I want you guys to be with me and to continuously answer whatever questions I'm asking you guys. Okay, so let's consider a situation in which there is a particle of charge, let's say q1, and we have clamped this particle. Okay, so we have clamped this particle, so this particle is fixed. Okay, this particle is fixed. All right, now we have another particle which is present at some distance from it. This particle is also positive and it has a positive charge. Its charge is q2. Let's say its mass is m. Okay, and imagine a gravity free space, which basically means that there is no effect of gravity, like there is no weight that will come into play. Okay, now suppose if I release this charge. Okay, so let me also give you the initial distance between the charged particles. Let this distance be d naught. Okay, so guys, suppose if I just release this charge from this point, what do you think will happen? Do you think that the charge will remain at rest? Do you think that if I release this charge, it will remain at rest? What is your opinion, guys? In case if you are thinking that it will remain at rest, then you are wrong, guys. How do we make this judgment? We think in terms of the FBD of the particle. So you have to imagine that how many forces are acting on this. Okay, I think. Okay, so we have to think about how many forces are acting on this particle. Okay, so right now there is only one force which is acting, and that force is the electrostatic repulsion due to this particle. So there is one force, and therefore the net force is non-zero because there is no other force which can balance this one. Okay, so once we release the particle, under the influence of that force, it will start moving in this direction. Okay, now imagine that it will start moving. So will it continue to move with a constant acceleration? So I think you will be able to judge that the acceleration depends on the force, and the force on this depends on the distance, because the force is electrostatic force. The distance is changing, therefore the force is changing, therefore the acceleration is changing. Okay, so we have to first ask ourselves that, okay, whether there is any acceleration or not. Yes, there is acceleration. Now, is that acceleration constant or not? So the acceleration is not constant, it is a varying acceleration, which basically means that we cannot make use of the equation v is equals to u plus at, s equal to ut plus half at square, and v square equal to u square plus 2s. All those equations that we derived for the case of constant acceleration, those equations are not applicable here. All right, so that is not applicable. Now, what can be asked in this situation? So that is a situation. I have not yet told you the question. So let us think that what can be the possible question pertaining to this situation. So one of the possibilities is that the question may ask you that, okay, by the time this particle reaches a distance x from the clamped particle, what is the speed of this particle? So that seems a very plausible question. Okay, so we want to know the speed of this particle by the time the distance between the two particles has changed from d naught to x. Okay, now people, what are the things that you have to keep in mind? So the first thing, acceleration is varying, so I can't use v square equals to u square plus this point to this point. Okay, there is no collision that will take place. Guys, I hope you can hear and see me. Okay, so there is no collision that will take place. Okay, guys, can you hear me? I'm not sure whether there is some issue with the connection or something wrong is going on with the screen. Something else is going on here. Okay, let me try to fix it, guys. Mm-hmm. Guys, people, things are not working out. I think the screen is gone. I think some problem is there. Can you come on? Huh? Okay. People, I think. Okay, I think we are back in business. Yes or no? Okay, so it was having problems. Okay, so it was having problems. A lot of problems. Huh? Hmm? I think it's fixed. Okay, people, are you there? I'll continue now. I think it is fixed now. So I'll continue. So we were talking about that what will be the speed of this particle as it has moved to a distance x, and I told you that we should be using the work energy theorem. So there are two conditions that you can check before you start using work energy theorem. The first one is whether there is any collision which is taking place or not. So I don't see any collision taking place here. That is one thing. And second thing, you will not be able to use work energy theorem for any time related calculation. For example, if the question asks about how much time will it take for this particle to travel from this position to this position, then we will not be able to use work energy theorem. So time is not asked, collision is not taking place, work energy theorem, we are good to go. So let's use it. So we'll solve this. So work energy theorem states that external work plus u initial plus k initial is equals to u final plus k final, right? So whenever we are trying to use this equation, we have to first identify an initial moment and a final moment. Here we can choose this as the initial moment and we can choose this as the final moment. Like initially we released the ball and we released the particle, it was at rest, and then it started traveling, and as it has traveled some distance, it acquired a speed of v. So let that position be the final position. Now the next thing that we have to think, once we have assigned the initial and the final positions, next thing we have to think whether there was any external force acting on the system. So here the system is the two particles, so they are our system. Now the question is whether there has been any external force acting on the system. What do you think, guys? Is there any external force? See, if these two are part of our system, then any force that these two exert on each other, that will be considered as an internal force. So the force experienced by this particle is an internal force, but this particle is not moving despite the fact that the other particle is exerting a force on this. This is not moving, which basically means that the force by the other particle is getting balanced by the force exerted by the clamp. So the clamp is definitely exerting some force on this, and that force is the, I hope you can see and hear me, okay, and that force is the external force. So there is definitely external force on this system. Now this external force, is it doing any work? The answer is no, because this force is acting on the particle and this particle is not moving at all. So although there is external force, but it is not doing any work because the displacement of the point of application of force is zero. Okay, so let's come back. So work done by external force, that is zero. Force is there, but the work done by the force is zero. U initial, so we will write potential energy by looking at the initial figure. Initially these two were separated by a distance g naught. In previous class we learned how to write the potential energy, so I'll follow that. So that will be K into the product of charges divided by the distance between them. Okay, and then initial kinetic energy. So at the initial moment, both the particles were at rest. One is permanently at rest and the other was also at rest. We released it from rest. U final will become K Q1 Q2 by X, and then final kinetic energy will be half mv square. So from this equation we can rearrange and we can get the value of v as a function of x. So we will get K Q1 Q2, okay, and then 1 upon d naught minus 1 upon x, okay, and then 2 will come here, m will go down, and root of this. So that is the expression of v as a function of x. Okay, so that is how we can obtain v as a function of x. Now guys, what else can be asked in this question, or how else this question can be modified? Okay, so one of the things that I can ask is that, okay, this particle is traveling, so as it is going away, its speed is increasing. What will be the final speed of the particle? What do I mean by final? So guys, as x increases, it may ultimately become infinite, and when it becomes infinite, okay, then I can say that the particles are now so vastly distant from each other that they will not influence each other anymore, and therefore the speed of this particle will stop increasing. Okay, which is mathematically, it can be seen from here also. If I put x tends to infinity, then I am left with a certain number, all right, and that will become the final speed. Like, so v final, you can say v, the final speed that the particle will get, it will be 2k q1 q2, okay, by m into d naught, by putting x as infinity. Okay, so that was one question that we can do. Now we can make a slight modification in this question. If you want, we can make a slight modification. The same question can be asked in the other manner. Like, if we release the particle, starts moving in this direction, what if I project this particle and then I see whether this particle can hit the other particle or not? So let's try to investigate that. Okay, so our next question would be, this is a particle of charge q1, and let's say it is clamped, and we will try to see whether it is possible to hit this particle with another particle by projecting it with some velocity, and this particle is also having a charge q2. Again, both are positively charged. Okay, so if I throw this particle towards q1, do you anticipate that this particle will start slowing down because of the repulsion from this one? Okay, and if it does start slowing down, when does it come to rest? Okay, so if it doesn't come to rest by the time distance between them becomes zero, then it means that this particle will hit the other particle. I want to investigate whether it hits or not. So what I'm going to do, I'm going to say that, okay, let us assume that this particle comes to rest at a distance, let's say d minimum. Okay, so if I see a mathematical possibility of getting d minimum as 0, but that external force is not doing any work, okay, so I will write w external plus ui. Now ui will be given as k q1 q2 by d naught, the initial kinetic energy. So this time initially we gave some kinetic energy, so that would be half mv naught square. Final potential energy will be k q1 q2 by d minimum, okay, and final kinetic energy will be 0 because ultimately this particle would have come to rest. Now we will solve this, we will rearrange to get the value of d minimum. So it would be what? It would be k q1 q2 divided by k q1 q2 by d naught plus half mv naught square. Okay, yeah, that's d minimum. Okay, Now, how can I get d minimum as 0? Okay, how can I get d minimum as 0? So guys, if I have to get d minimum as 0, I need to make the denominator infinite. Now, these are all finite numbers. It means that I will have to throw with infinite speed, which basically means that we can't get the denominator to be 0, which means that it is not possible to throw this particle with any amount of speed and ensure that this particle hits the other particle. So they are not going to collide ever. So the minimum distance between them will be given by this. Okay. Now guys, let's increase the difficulty level a bit further. Okay, these two problems that we have done till now, they were both similar. Okay, we will now increase the difficulty level conceptually. Like conceptually, we'll go a level higher. So what change I'm going to do in this question is that, let's say this is a particle of mass m and charge q. So for the sake of ease of calculation, I will choose another identical particle of mass m and charge q, and let's say they were separated by a distance a. They were initially separated by a distance a. Now again, imagine that there is no gravity and we have released the particles. Okay, we have released the particle. So tell me guys, if there is no gravity and we have released the particle, what will happen? Will both of them continue to remain at rest, or will both of them start traveling, or will only one of them travel? So guys, this time we have not clamped any of the particle. Okay, so we can see that whatever is going to happen, it will happen to both the particles. Situation is symmetric with respect to both particles. So whatever happens to one particle, identical thing will happen to the other particle. So after a while, if we see, we will see that the particles are moving. So if this particle would have traveled some distance, then the other particle would also have traveled some distance. If this particle is traveling with the speed v, then this particle would also be traveling with the speed v. Okay, and now let's say the distance has changed to, let's say, eta times of a. So we may be asked the value of v. Okay, so again we can write work energy theorem and get the value. If we further want to make this question a bit difficult, what we can do, instead of giving the masses as same, we can actually change the masses. We can make the masses as, let's say, m1 and m2. Now what difference will this create in the question? If you choose the masses to be different, then we have disturbed the symmetry. Now we can no more use the argument of symmetry to declare that if this is moving with the speed v, then this will also move with the speed v. Now we cannot do that, and we will be forced to assume that their speeds are different. Okay, so now they are moving with two different speeds, v1 and v2. What does that mean? This means that we have two unknowns now, and therefore we need at least two equations. Okay, now one of the equation will be energy equation, but that equation will have two unknowns, v1 and v2. So we need one more equation. Which concept will be responsible for the second equation? Think about this and tell me, how is this question different from the previous one? If you find the answer to this question, you will find the answer as to, like, to the question that what should be the second concept. Okay, the difference between this question and the previous question was, in the previous question, one of the particle was clamped, and the force exerted by the clamp on the particle became the external force. Now, because there is no clamp, there is no external force, and if there is no external force, we can talk about momentum conservation. So initially, when we release the particles from rest, the net momentum of the system was 0, and later on the net momentum has to remain 0. So this will become our second equation. Okay, so let me write the momentum conservation first. So m1 v1 is the leftward momentum. This should be equals to m2 v2, that is the rightward momentum. Okay, so that the net momentum is 0. That is one of the equation, and the other equation will be the energy equation. How will we write the energy equation? Work done by external agent is 0 this time, because the external agent is not even present. Okay, u initial will be given by k into q square. Remember, I assumed that the charges are same, divided by the initial distance a. The kinetic energy for both the particles was 0. U final will become kq square by eta times a, and then k final will become half m1 v1 square plus half m2 v2 square. So this is our two equations. This is equation number 1. This is equation number 2. We will solve them together, treating v1 and v2 as unknowns, and then we'll get the answer. So what you can do, you can substitute the value of v1 from this equation into the other equation, and then you can solve for v2, and that will give you the answer. All right, so that is another level of difficulty. So in the first variety of question that we did, one of the particles was clamped, the other was free to move, the other was moving, and because there was only one unknown, we were happy with one equation. This time, because both particles are moving, they may have different speeds depending upon the masses. So we will be forced to use two concepts, and we have done that. One of the concept would be conservation of linear momentum. The other concept would be conservation of energy, or you can say work energy theorem. Okay, now let me give you a similar question again. This time, I want you to judge what is to be done by yourself. Okay, so let's say the situation is this. So there is an equilateral triangle. Okay, there is an equilateral triangle. Does it look like equilateral triangle? Yeah, more or less. Okay, and at the vertices of an equilateral triangle, there are three identical particles kept: mass m, charge q, mass m, charge q, mass m, charge q, and the side length is a. Let's say the side length is a. Okay, this is the side length. Okay. Now, if we release the particle, my first question to you all: what happens? If we release this particle, what happens? Okay, so if we release these particles, guys, are you able to judge that they will all start moving radially outward? Again, the symmetry of the situation suggests that this will happen. So they will all start moving radially outward, which means that we will see the triangle to be expanding. We will see the triangle to be expanding, and we can actually ask this question that by the time the triangle becomes a bit larger, okay, let's say the triangle becomes eta a in side length, by that time what is the speed of the particle? So this would be traveling with v, even this would be traveling with v, even this. So guys, can you try this question yourself, guys? If you are watching this session in replay, I want you to pause the video here and then try this question yourself. Okay, again, the symmetry of the situation helps us to declare that all three are moving with the same speed v, and therefore we have only one unknown to deal with, and we can write energy equation to deal with that unknown. How will we write the energy equation? The external work is 0. The external work is 0 because there is no external force. Now U initial. So guys, we have three particles, and out of three particles, how many pairs can be made? Count how many pairs can be made. So a total of 3 pairs can be made. I need to write the potential energy of each pair. So I will write k q square by a. So that was the energy of this pair. Then again this pair and then this pair. So 3 pairs will be there. So I can rather just multiply this with 3 because all the pairs have the same energy. So I multiply this with 3. The initial kinetic energy was 0 for all the particles. Now finally what has happened? Again we will write kq square by eta times of a into 3, and then again if I write kinetic energy, then I will have to write kinetic energy of all the 3 particles. I will write it like this, and now I will do the math to get the value of v, and that would be my answer. All right, so again this question was an extension of what we did in the previous question. Only instead of 2 particles we are now having 3 particles. Okay, now let's increase the difficulty level a bit further. Okay, let's go a bit further now. Okay, so now again let me clamp the particle. So this is the particle of charge q which is clamped, and what we plan to do is somewhat like this. So we plan to throw another particle, positive particle, okay, of let's say charge small q, mass m, with a speed v naught along a straight line which is at a perpendicular distance d naught from this. Okay, so this is my intention, and we are throwing this particle from far away. So this symbol indicates a broken line, indicating that the line is too long to be drawn on the board, and therefore we can consider this particle to be at infinite separation. Okay, now imagine guys, there is no gravity. You have fired the particle along this straight line. Are you anticipating this particle to continue moving along this straight line? Do you imagine that? Okay, because I don't imagine that. In my opinion, it may start its journey along the straight line, but then as it comes closer to this particle will repel the other particle, and therefore the other particle will follow a trajectory somewhat like this. It will ultimately move and then it will go to infinity. Okay, so if that is the case, then what we understand is that this particle was getting closer to the clamped particle, and then it started moving away. So it would be a logical thing to ask that at what moment or what was the minimum distance between the 2 particles. Okay, so the particle came closer, then went away, and it did not collide. So it did not collide means the distance between the particle never went to 0. It was always non-zero. So what was the minimum distance that we got between the two particles? That is the question. The most important aspect of this question is to identify the point where we can declare or whether we can assert that at this position the distance between the two particles was minimum. So what do you think, guys? Is this the point where the distance was minimum? Is this the point? Is this the point? Is it beyond? So what is the speciality of that point where the distance will become minimum? If you have figured it out, tell me. Dropping a perpendicular to the path, do you think that this will do the job? So when this particle was moving from here, at that moment the distance was minimum. Can we say that? Okay, so that was the first important aspect of this question, to identify that when was the distance minimum. The second aspect is, at this point the particle will have a different speed as compared to with which we projected it. Okay, because as the particle was coming closer, it was slowing down also. So we can expect this v to be different from v naught. So again we end up with two variables. There are two variables now. I don't know v, I don't know d minimum. I need two equations. One of the equation can be energy equation. What will be my other equation? Momentum conservation? No. This particle is clamped, which means there is external force on the system. You can't conserve the momentum. Then what? What do I do now? Guys, you can't conserve the linear momentum, but notice one thing. As this particle was moving through various points, it was always experiencing a repulsive force like this. Okay, it was always, so the force on this particle was always passing through this point, which means that the torque about this point has always been zero, which means we can conserve angular momentum about this point. Alright, so now we will use angular momentum conservation about this point and energy equation to get the answer. So how do I write the angular momentum conservation? So guys, any conservation equation will always be written by considering an initial position and a final position. So in the initial position, this was the line along which we projected the particle. So the momentum was along this line. We will write m v naught, and then we multiply with the perpendicular distance of the line of motion from the point about which we are conserving momentum. So we'll multiply with d naught. Similarly, at this position, this is momentum mv naught, mv, and this is the line of motion. So perpendicular distance is d minimum. Okay, so this will become one of the equation, and the other equation will be the energy equation. So initial, see, work external is zero because external force is there, but that force is not doing any work. U initial is zero because the separation was large. Okay, K initial was definitely there. So initially we provided some energy to the particle. Final potential energy, now the distance is finite, so there will be a potential energy, and that would be K capital Q small q by d minimum. And then what was the final kinetic energy? It would be half mv square. So you substitute the value of v from here to here, and then you solve for d minimum. That will give you the minimum distance between the two particles. Alright, people. Okay. So that is the third concept that we have looked into. Alright. So guys, we have considered three different situations. In one situation, one of the particle was clamped and the other particle was projected directly towards the first particle. Okay, so that was one situation. The next one was both the particles were free to move. When such is the case, when all the particles are free to move, we rely on momentum conservation and energy conservation. And then there can be another case in which one of the particle is clamped, but the other particle is not projected directly towards this point or away from this point. It is given a velocity at a different line. In this case, you have to go with angular momentum conservation and energy conservation. Alright, people. So this was the the different variety of questions that you can get as part of questions on potential energy in electrostats. I'll stop here now. In the next session, guys, I'll start with a new chapter, most likely magnetic effects of current. So I'll see you next week, everyone. Take care. Bye bye.